In this lesson, we will be talking about how to differentiate inverse functions, both in a generic way and at specific points. But before we get started, we want to discuss and review what are inverse functions and some other facts about them. So inverse functions, as you may recall, are two functions where you switch the inputs and outputs. So you may remember that as the fact that the x's and y's are switched using those two variables. The more formal definition, however, though, for inverse functions is if I have some function f and its inverse, written like this. So if I have f, I would refer to f's inverse with this notation. Well, f of f inverse of x is equal to x, and f inverse of f of x is equal to x. So that means that if I compose a function and its inverse, both directions, so both this way and this way, that whatever input I put in, I should get that same input after I've done composing. So essentially these two functions, operations or whatever's being done to these two functions, are undoing each other, and I get the same output as I put in. So graphically, you may be able to identify two functions if they're inverses, or just to get a hunch about this relationship is the fact that when you look at these two graphs, that they are a reflection of each other over the line y equals x. And again, that's a consequence of switching the inputs and the outputs, or the x's and y's. If you're given an equation for a function and you want to be able to find its inverse, the algorithm that you've learned for that back in Algebra 2 was that you first start by switching the input or the output, or switch the x and the y. Okay. We want a function or equation solved for the dependent variable. So once you've switched the x and the y, generally at that point then you've solved for y equals. Okay, not all functions have an inverse that's also a function. If you recall how you'd be able to check this, or check one-to-oneness, is one way to do that quickly is the horizontal line test. So if you're looking at a particular function and you graph a horizontal line anywhere at any particular y value, if it only intersects the function once, that means that function will have an inverse that is also a function. Okay, so let's just kind of review. For instance, how do you show f of x and g of x are inverse functions? So what we would need to do then is to compose them to show that overall, if I put in an x, I just get out an x. I know in your mind you might be thinking, well, why can't I just find the inverse of f and show that that's equal to g? Well, that's a way to perhaps verify it, but using the formal definition, we do have to use this idea of compositions to be able to show that f of g of x is equal to x and g of f of x is equal to x. And I do have to show both of those to really show or prove this process. So order not being important, I'm going to go f of g of x. So f of 1 minus x over x. So what I'm going to do then is that means that 1 minus x over x needs to go in as my input right there. All right, so I'm going to have 1 over, and then instead of putting down an x, I need to input what g is. All right, so then I've technically done the process, but I do need to show that I get x out. You do need to show the simplifying steps. You can't just say, bam, this equals x, because you want whoever is reading this to make sure that they understand where your work is coming from. So I have some rational expressions in the bottom there, so I need to get a common denominator. All right, so in the bottom there, I end up getting when I combine these two, I end up just getting the x's end up canceling, and I end up with 1 over x, because 1 minus x plus x, the x's cancel, so just 1 over x. And 1 over x is just equal to x. All right, so then what I just showed is that when I input an x, I first plug that into the function g, and then plug that into the function f, that those two functions overall cancel each other out, and I end up with the same output as I put in originally. So now I also need to show that g of f of x is equal to x as well. All right, so g of 1 over x plus 1. So that means everywhere in G I have an x, I need to input that. So 1 minus 1 over x plus 1 all over x plus 1. So I need to multiply this here by x plus 1 over x plus 1. So on top, if I want to do a little bit of simplifying, that can turn into x plus 1 minus 1 all over x plus 1 all over x plus 1. If you notice, the 1's will cancel. And so you're left with x over x plus 1 on top. And then dividing by x plus 1 here is the same as multiplying by the reciprocal. So the reciprocal, oops, I'm missing my 1 over right here. Pardon me. So dividing by 1 over x plus 1 is the same as multiplying by its reciprocal. So the reciprocal of that would be this. And I end up just getting x. So I was able to show that f of x and g of x are inverse functions. Graphically, if we go ahead and take a look at this, I have it plugged into my graphing calculator here. So notice in my y equals I have f, and in my y3 I have my g. Recall that two functions, a way to tell if they're inverses or not is they might be a reflection over the line y equals x. So let's just go ahead and take a look at the graphs just so you can maybe see that relationship. So there's f. There's the line y equals x. And if you can see that f is being reflected over the line y equals x. So for instance, you can kind of see that like a point here is being reflected over here. Okay. So let's go ahead and actually practice finding an inverse function to review that process. So recall that I had said that the first thing you need to do is switch your inputs and outputs. So if this were y equals or f of x equals, I would switch it to x equals y cubed minus 1. So then I would want to solve for y equals, so I add the 1 to the other side. And to get y by itself, I need to get rid of that third power, and to cancel the third power, I would need to do a cube root. Oops. So I end up with y equals the cube root of x plus 1. If I want to rewrite that using the inverse notation, the inverse of f is equal to the cube root of x plus 1. If we want to verify that result graphically, just to take a look at it, so let's go ahead and graph those two. Okay, so I'll plug in x cubed minus 1. The line y equals x, I'll put that in there. And then the cube root of x plus 1. So there's x cubed minus 1. So there's the line y equals x. And then here's the cube root of x plus 1, and you can see indeed that those two functions are reflections of each other over the line y equals x. All right, so let's go ahead, as long as we've got this open, maybe take a quick look at that table. All right, so recall that you're switching the inputs and the outputs when you're working with inverse functions. In my y1 is x cubed minus 1, y equals x is in my y2, and in my y3 I have the cube root of x plus 1. So inputs and outputs are switched on inverse functions, so I just want to kind of review that looking at a table. So it doesn't really matter what point you pick, because I'm just trying to kind of review this tabular method for looking at this. So let's say we were to plug in an x value of 4 just to pick something. So if I were to plug 4 into y equals x, so x cubed minus 1, 4 cubed is 64 minus 1 is 63. All right. Well, I would expect then if I were to plug 63 in, that notice that I get 4 as an output in its inverse. So notice that if I have the point 463 on the first function, that I would have the point 634 on the second function. So we'll be using all of this information to work towards derivatives. All right, so just to kind of go over some of the basics real quick, let's say if we have a function whose domain is on the interval I, if f has an inverse function, then let the following be true. If f is continuous on the domain, then so is its inverse. Okay, so if a function's continuous, so is its inverse. If f is increasing or decreasing on the domain, so is f inverse. So what that means is if f is increasing, f inverse is also increasing. Similarly, if f is decreasing, its inverse is decreasing on the interval. And if f is differentiable on the domain and not equal to 0, then f inverse is differentiable also. All right, so let's start off with a function that's pretty easy to work with, that you're pretty familiar with. So we're going to look at half of the parabola f of x equals x squared on the domain x is greater than 0. What I want to do is I want to find the derivative of its inverse and just look at some derivatives at specific points. Okay, so I have f of x equals x squared graphed in blue there. All right, so let's just go ahead and right off the bat just figure out what the inverse of f is. So that's probably something you're familiar with there. So if I were to switch x and y and solve for y equals, when I get rid of the square, I end up with plus or minus, but I only want the positive square root of x because I'm only looking at half of the parabola here. That's what forces the inverse to actually be a function and pass the vertical line test. All right, so let's go ahead and say that f inverse is equal to the square root of x, and we're supposed to look for the derivative of that. So if I go ahead and take the derivative, so the notation gets a little heavy there. So I'd have 1/2 x to the negative 1/2. You can leave it like that with the exponent, or you can rewrite it as 1/2 square roots of x. Well, let's just kind of look for some patterns that'll help us understand the general rule for looking at derivatives of inverses. So if I have the point 0.24 and the point 0.42 and try to look at the derivatives there, if I want to look at the original function, the original function's derivative, the derivative of x squared is 2x. So f prime of 2 is equal to 4. And then if I were to look at the inverse's derivative at 2, so if I were to go ahead and plug 2 into this equation right here, I get 1/2 square roots of 2. Okay. Well, they also asked us to kind of plug in both of these values here, so let's also look at f prime of 4. F prime of 4 is equal to 8, and f inverse prime of 4 is equal to 1/2 root 4, which is 1/4. So just kind of taking a look at these, there actually is something in common between these, or a pattern that could be noticed. We would maybe need to do a little bit more, but let's kind of hold that thought here for just a second. So let's try the same process at 3, 9, and 9, 3. So f prime of 3 would be 6. f prime of 9 is 18. F inverse prime of 3 would be 1 over 2 root 3. And f inverse prime of 9, 1 over 2 square roots of 9, which would be 1/6. All right, so the pattern that we could, if you can kind of take a look at this, is so if I'm looking at inverse values, because 3 and 9 are where the input and output would be switched, it appears that the slopes are reciprocals of each other. So that's actually how you can be able to take the derivative of a function, its inverse, in a more general form, or the pattern that can be used to discuss that. All right, so let's go ahead and look at this more formal explanation here. It says that the derivative of an inverse function, let f be a function that is differentiable on the interval I. If f has an inverse function g, then g is differentiable at any x for which f prime of g of x is not equal to 0. So the derivative of the inverse is equal to the reciprocal of the derivative of the function with the inverse inputted. I actually prefer to rewrite this not with f's and g's, but with f and f inverse notation, just because I personally find that easier to follow. I don't know, you may think it's less complicated. So the derivative of an inverse is equal to 1 over f prime of f inverse of x. I hope that as we go through this, that this makes sense. So if I'm looking at a function's inverse, and I want to find it a specific value, I would need to do the inverse of that function at that point, because we do want to work with inverse functions. And the reciprocal part comes in, and this is kind of interesting, or should hopefully be easy to understand. Why is it reciprocal? Well, remember that we're switching inputs and outputs. That's what inverse functions do. You're switching inputs and outputs. Well, if we're looking at a derivative, which is the slope of a tangent line, slope is rise over run, or vertical change over horizontal change. Well, if I'm switching inputs and outputs, I'm switching x's and y's, I'd flip the slope. I'd flip the change in y over change in x. So that's why that there's a reciprocal as a part of this formula. If you can understand better where the formula or the concept is coming from, it'll help you execute it better and remember it for future use. Okay, so let's just see how this works using the example that we just looked at, f of x equals x squared. So I have the equation up here, and again, if you would prefer to see that using this notation, that's fine also. All right, so it says, find the derivative of the inverse of f. All right, so there are some parts of the formula that we need to do that'll help us along. So if we're going ahead and taking a look at this, we need to know what f prime of x is. So f prime of x is equal to 2x. We also need to know what the inverse function is. So we had said that the inverse function was the square root of x. So following the formula that's up here, let's go ahead and follow that notation. So I'm going to go ahead and substitute in the inverse of x being the square root of x, and the derivative is 2x. So 2 with an input of square root of x. So that's how I would use the formula that we just learned to find the derivative of an inverse. On a side note, if you recall, we had known that the inverse of x was equal to the square root of x, and we had found that the derivative of this inverse was also equal to 1 over 2 root of x. So that was on one of the last examples. So you do get the same result. So you might be asking yourself, if I already know what the inverse function is, why would I want to use this formula? To be honest, if you already know what the inverse function is, I don't really have a preference for how you find the derivative of the inverse, because in mathematics we do want to do what's most efficient, what makes the most sense to us. But this idea of knowing that the derivative of an inverse is the reciprocal of the derivative at that inverse value is something that you do need to know. It is a topic that you need to know for future study of calculus and for the AP exam. Um, so I am going to practice using this notation just so that we have a better understanding of that. Okay, so let's look at some function f of x equals 1/4 x cubed plus x minus 1. We're going to find the derivative of the inverse at 3, so that's our ultimate goal. Um, so it says remember, looking at the formula, one of the things that we're going to need to be able to find is we need to know the derivative of f, and we also would need to know the inverse function and this time we're working at a specific point. One of the reasons we would want to know this formula is if we were to switch the x and the y, we wouldn't even be able to solve for y equals. So when we're looking for this at the specific value, I want to keep that in mind as well. Okay. So one of the things we need to know is the derivative of f, so we can go ahead and find that. So if I bring down the 3, I have 3/4 x squared plus 1. I need to know f inverse of 3 as well. That's what they're asking right here. So what that means is I need to know this is no longer an input, it's becoming an output. So I want to know, essentially, this is what we're asking. At what y value is this? Or at what input it's switching has an output of 3. So there's many different ways that you can think about this. But so whether or not you have an x or y here might have to do with your understanding of this. I don't want to try to confuse you at all. It just depends on whether or not you're talking about the original function or its inverse. So essentially, what input has an output of 3? Because we're reversing the roles here. So you wouldn't be able to solve this cubic necessarily algebraically. So you would want to use your graphing calculator. On something like the AP test, on like a multiple choice question, they would give you a table of values, or it would be on the calculator part of the test. So I graphed the cubic, and I also graphed the line y equals 3. And I found that they intersected at the point 2, 3. So what that means is that f inverse of 3 is equal to 2. So if I want to find the derivative of the inverse at 3, that's going to be 1 over f prime of f inverse of 3. So 1 over f prime of 2, because we said that this was equal to 2. Okay, so the derivative, we said that that was 3/4 x squared plus 1. So 1 over 3/4 times 2 squared plus 1. So that ends up simplifying out to be 1/4. Okay, let's look at one more example. So f of x equals 2x squared minus 3 for x is greater than 0. Find f inverse prime of 3. All right, so then I would want to know what f prime of x is, so that's something important. So for x, I would also need to find f inverse of 3. So this one can be found algebraically, so if I switch this to being an output, so I add 3 to the other side, divide by 2, square root of 3. All right, so let's go ahead and find f inverse prime of 3. All right, so I have 1 over f prime of f inverse of 3. So I'm going to do 1 over f prime of the square root of 3. F prime is 4x, so 1 over 4 root 3. And you don't need to rationalize that necessarily. I mean, you certainly can choose to. Okay, last but not least, let's look at something we've worked with recently. So natural log of x and e to the x. Let's just kind of show that using the information that we learned today, um, that the properties that we've learned to be true earlier in this chapter can be held up. So we know, let's say that f of x equals natural log of x, and that its inverse is e to the x. So let's just kind of practice again by doing the derivative of a function's inverse is equal to the reciprocal of the derivative of the inverse at that point. So recall again that one of the things that we're going to need is the derivative. The derivative of natural log of x is 1 over x. Okay, and then we know that the inverse is e to the x. So 1 over f prime of e to the x. The derivative is 1 over x, so 1 over e to the x, which is just e to the x. So what we've just shown is that if f of x is natural log of x, we know that the derivative of the inverse of natural log of x is e to the x. Well, we know that to be true, because if the inverse of natural log of x is e to the x, we know that the derivative of e to the x is e to the x. All right, so in this lesson, we've just done a basic review of what inverse functions are, how you would prove two functions are inverse, how you could see that graphically in looking at a table if this idea of inverse inputs and outputs are switched. And then we went through generally how can you find the derivative of an inverse using the general formula.